In this video, I am going to discuss about Carnot's theorem. The Carnot's theorem consists of two statements. Okay, let us see one by one. That is, the first statement is no engine working between two given temperature can be more efficient than a reversible or Carnot engine working between the same two temperatures. This is the first statement, that is, no engine working between two given temperature can be more efficient than a reversible Carnot engine working between the same two temperature. And the second statement is all reversible engine working between the same limits of temperature have the same efficiency whatever be the working substance. This is the second statement, that is, all reversible heat engine working between the same limits of temperature have the same efficiency and whatever may be the working substance. These are the two statements given by the Carnot theorem. Let us explain the first statement. That is, here I am going to consider a source which is at temperature T1, and then I am going to consider a sink which is at temperature T2, and here I am going to consider IR as an irreversible heat engine and R as a reversible heat engine, and here T1 is greater than T2, and here irreversible heat engine is having efficiency eta 1 and reversible heat engine is having efficiency eta 2. And here, even though these two heat engines are working between two temperatures T1 and T2, here efficiency of the reversible heat engine is greater than the efficiency of the irreversible heat engine. This is the first statement of Carnot. Okay, now let us see second statement, that is, here also same we are going to consider source which is at temperature T1 and sink which is at a temperature T2. Here also same, T1 is greater than T2, and here I am going to consider two reversible engine R1 and R2. R1 and R2 are reversible heat engines, and these two reversible heat engines are working between same two temperatures, and here eta 1 be the efficiency of the heat engine R1 and eta 2 is the efficiency of the reversible heat engine R2, and here eta 1 and eta 2 are equal. That is, here all reversible heat engine working between the same two temperatures have the same efficiency, whatever may be the working substance. That is, here let us suppose this heat engine R1 is working with diesel, and let us suppose R2 is working with steam. Here working substance is different for both reversible engines. Here the efficiency of the both reversible heat engine is same, even though the working substance is different for different reversible heat engines. It does not depend on working substance, it only depends on the temperature. This is the second statement of Carnot's theorem. Okay, let us prove first statement, that is, no heat engine is more efficient than a Carnot engine. Here, to prove this, I am going to consider a source which is at temperature T1 and a sink which is at temperature T2 and irreversible heat engine and reversible heat engine. Here irreversible heat engine absorbs Q1 amount of heat from the source, and it rejects Q2 amount of heat to the sink, and it do some amount of work W by absorbing Q1 amount of heat, and here the amount of heat rejected is equals to Q1 minus W. Here also same, the reversible heat engine absorbs Q1 dash amount of heat from source, and it do some amount of work W, and it rejects Q2 dash amount of heat to the sink, or which is equals to Q1 dash minus W amount of heat is rejected to the sink. Carnot theorem states that efficiency of reversible heat engine is more efficient than efficiency of irreversible heat engine. This is the statement of Carnot's theorem. Here, to prove this, we are going to use a contradiction method. That is, we are going to consider efficiency of irreversible heat engine is greater than efficiency of reversible engine. We are going to assume this, and we know that efficiency is equals to the amount of heat added to the system Q1 and the amount of heat rejected by the system Q2 divided by amount of heat added, or Q1 minus Q2 gives work done divided by Q1. Here, in place of efficiency of irreversible heat engine, I am going to add Q1 minus Q2 divided by Q1, which is greater than Q1 dash minus Q2 dash divided by Q1 dash. Here let us replace Q1 minus Q2 by W divided by Q1 greater than W divided by Q1. Here the work done by irreversible heat engine and reversible heat engine are same. So this equation becomes Q1 dash is greater than Q1. Finally, we left with this equation. When we consider efficiency of the irreversible heat engine is greater than reversible heat engine. Efficiency of the reversible heat engine. Or we can write it as a Q1 minus Q2 is equals to Q1 dash minus Q2 dash, because the amount of work done is same. Okay, here this is the first situation. Now let us take the second situation. That is, in second situation I am going to consider a source which is at temperature T1 and a sink which is at temperature T2, and here T1 is greater than T2. Here also same, I am going to consider a irreversible heat engine. Here reversible heat engine. In second situation, the irreversible heat engine, it absorbs Q1 amount of heat from the source and it does some work W and it rejects Q2 amount of heat to the sink, or we can write it as a Q1 minus W. In second situation, the reversible heat engine, it absorbs heat from the sink and it rejects heat to the source. That is, it working as a reversible heat engine. That is, here it is going to absorb Q2 dash amount of heat, that is, which is equals to Q1 dash minus W, and it is going to do some amount of work W, and it is going to reject Q1 dash amount of heat to the source. But here, to work reversible heat engine in the reverse direction, here we need to supply some amount of work. Then only this reversible heat engine is going to absorb heat from the sink and it rejects to the source. To do this, we are going to give some amount of work done W from irreversible heat engine. The amount of work done by irreversible heat engine is given to the reversible heat engine. Then only it is going to absorb amount of energy from sink and it is going to reject to the source. And the net result of the complete cycle of the coupled engine is given by, that is, gain of heat by source, that is, this is the gain of heat, that is, which is equals to Q1 dash minus Q1. This is the net heat gained by the source, and loss of heat by sink, which is equals to Q2 dash minus Q2, or we can write it as a Q1 dash minus W minus Q1 plus W, or Q1 dash is equals to Q1. Here the amount of heat gained by source is equals to Q1 dash minus Q1, and the amount of heat lost by sink is Q1 dash minus Q1. Let us suppose irreversible heat engine and reversible heat engine are coupled, that is, we are going to take it as a single engine. Here we have given Q1 dash minus Q1 amount of heat from sink to this coupled heat engine, and it rejects Q1 dash minus Q1 amount of heat to the source. But in practice, to flow heat from colder body to the hotter body, we need to do some amount of work. If we do this work, then we are going to observe that there is loss of heat energy. But here we can see that the amount of energy absorbed and the amount of heat rejected are same. So here the work done is 0. So it violates the second law of thermodynamics. So this concludes that our assumption eta IR greater than eta R is wrong. So it implies that efficiency of the reversible heat engine is greater than efficiency of irreversible heat engine. And the second statement of Carnot's theorem is proved by the same argument, and for this purpose we consider two reversible heat engines R1 and R2. Here we consider two reversible heat engines R1 and R2, and we assume that the efficiency of the R2 is greater than R1, and from this experiment we conclude that R2 cannot be more efficient than R1, and therefore reversible engine working between the same two temperatures have the same efficiency, and hence the efficiency of the reversible engine depends only on the temperature between which the engine is working, and it is independent of the nature of the substance used.